Hello and welcome to the Metrology webinar hosted by NTMA's technology team. My name is Mike Hirsch. I'm NTMA's tech team leader and I'm honored to be your MC today. The technology team's mission is to provide accurate and timely information on current and emerging technologies that can improve productivity, competitiveness, quality, and profitability among the NTMA membership. One of the ways we do this is by hosting relevant technology webinars. Topics we choose come from you, our membership. So if you'd like us to cover a topic that's important to you, just shoot us an email, pick up the phone, or type us a note in the chat box. We value your time and promise to start and end on time as well. If you haven't already done so, please enter your audio PIN number that you received as you signed in. The format is pound, PIN number, and pound. This will help us provide the highest quality webinar for all who are attending. Today's webinar will help you discern when to use dedicated metrology equipment versus a universal CMM. And we are honored to have two of our industry partners on hand to present today's webinar. Mike Kambitz from Zeiss and Dr. Mark Malberg from Digital Metrology. Mike Kambitz holds the bachelor's degree in business administration from Eastern Michigan University and has over 30 years of metrology experience. He's held various roles ranging from application engineer to regional sales manager and has been with Zeiss for the last 20 years. Mike is a surface and form product specialist with additional training and expertise in both GD&T and Occam. Dr. Mark Malberg lives in a world full of surfaces. He is a surface metrologist with BSME and MSME degrees from Michigan Technological University and a PhD from the University of Warwick. Mark worked 10 years in industry as a corporate surface metrologist. Then in 1999, he formed Digital Metrology Solutions, providing custom metrology software development, training, and consulting. He's the developer of OmniSurf and OmniRound software packages, which are being used worldwide for the analysis of surface texture and geometry. His work and his software is incorporated into many commercial measuring systems. Mark is also active in ASME, SAE, and ISO standardization. He holds patents for various measurement and analysis methodologies and has published numerous metrology-related papers and articles. If you joined us late and haven't already done so, please enter the audio PIN number that you received as you signed in. Again, the format is pound, PIN number, and pound. This will help us eliminate unwanted audio distractions. If you'd like to ask questions, please use the chat box function on the GoToMeeting screen, and be sure to send to all. Our presenters will answer them in real time. So, without further delay, Mike Kambitz and Dr. Mark Malberg, thanks in advance for educating us on metrology equipment.
Thank you, Mike. So where we were kicking off, that you missed a great story. We're going to jump in and kind of give you a little bit of our experience on the topic of flexible versus dedicated gauging. Mike had a great story of people kind of landing somewhere in the middle.
Yeah, we had a customer that we dealt with a few years back that was a Chinese bearing manufacturer that was also doing testing at their facility. And as we went along through the sales process, it became evident that they needed multiple gauge systems to make the decision easier for them to do both 3D and 2D measurements that were a critical part of their business and the call-outs that were required on their drawings. So for the traditional purpose of three-dimension, they were deciding for the CMM to do size, control, and position location on a lot of their bearing components. In addition to that, they needed to have specialty analysis, which lent itself towards the surface and form products that were able to check 2D. And so from the standpoint of the surface and form products, they decided on a hybrid system with also a dedicated contour head. This gave them wide range 2D measurements as well as surface finish capability in the smaller macro world and micro checks for contouring. So it ended up being a combination of solutions to address their need for metrology relative to their components. So it's not always a all-or-one solution in many cases.
Sure. Yeah, a similar story on my side. I get to work with some really brilliant manufacturing people, and one particular customer of mine works in the measurement of surface finish, and he has evolved across both ends of the spectrum. Originally, some of these critical surfaces were being measured manually very near the process because it was so important to have accurate nearby data. But over time, they decided that they could move that away into a very flexible, very automated system. So it went from semi-dedicated to totally flexible, totally automated, but immediately after that, the need for close-by feedback showed up. Once in a while, you change a tool and you just want to know what that change did. So in the midst of spending a lot of money and installing a great flexible automatic system, they came back and bought a very inexpensive dedicated system to support those day-to-day quick questions, not the ongoing trend questions, if you will.
Yeah. So it went full circle for them.
It went full circle, so now they're actually using both.
Right.
It went from dedicated to flexible with a little bit of dedicated in the wings.
Right. Right.
So I'm going to hand it back to Mike here to talk a little bit about kind of the spectrum of gauging that's out there, ranging from crazy big flexible right down to small and inflexible, if you will.
Okay, thank you. So yeah, just to touch base, what we'll do is just highlight several of the reference systems that we'll be comparing and using for discussion in some of the talk points that will help us decide when we need a dedicated system versus possibly a universal CMM. Obviously, with the crowd that we have attending the presentation today, all of you are familiar with the universal system of a CMM. The CMMs have been around for quite a while. I won't get into all the details of the designs and capability and options, but we know that the 3-axis CMM provide 3 axes of movement with probe sensors that provide dimensional, size, location, and form on these machines. They're very flexible as far as their programming. Primarily they use tactile sensors, both single point touch and or scanning. I would ask that maybe some feedback through the chat device. I'd like to find out those users of CMMs, how many of them are using multiple probe systems, which I'll touch base upon, or just primarily have theirs equipped with a single touch probe system exclusively.
And there's a huge advantage to CMMs. You can make a video of them with your product underneath it, and it automatically makes you look really high-tech.
Yeah.
Because they're very cool to watch.
So the holy grail is the CMM per se. And then what we also have are the optical 2D and 3D measurement systems. These systems would be in the realm of video-based, projector-based, structured light systems that do 3D scanning. The optical systems are very powerful. They're flexible. They have a wide measuring range. Obviously, they're non-contact, which is very critical in certain industries today where destructive testing cannot be even considered. Then we have Surface Inform as our third grouping. Surface Inform products are kind of specialized dedicated gauges that are unique. They have a high fidelity of measurement, I'll say, with lots of data point scanning capability. But the main thing about Surface Inform products is that we're actually starting to delve into more of the process, looking at the fingerprint, the DNA of the process that the CMM in the macro world really can't evaluate. So they're dedicated, yet they're flexible and programmable, but they have their niche in supplying information that's necessary for process control. The next system based are the in-process machine vision and precision tools. In-process gauges and machine vision have been around for quite a long time, and as Mark had mentioned in his case study, they are near the process as well as in the process to provide direct, immediate feedback for inspection. These are special part application designed from the very beginning, and they are combined with hard fixtures and positioning techniques to give you some of the utmost accuracy and lowest uncertainty capable in metrology today. Then last but not least, the fifth group, which everybody's familiar with, is your traditional precision tools of a variety of design and purposes. Calipers, mics, bore gauges, thread and plug gauges, indicators, drop gauges, you name it. These are in the lab and yet can be near process and in process to give immediate feedback. Very easy to use, can be connected with SPC and or feedback to the machine, but they all have their purpose and sometimes in many instances are in lieu of CMM inspection. So these are the groups that we'll expand upon and some of the other critical areas that we need to identify.
Let me jump in real quick, Mike. So you're showing on the lower right a micrometer, a vernier caliper.
Yeah.
Pretty dedicated to one feature.
Correct.
But are they flexible?
They are flexible.
Isn't that strange? It's
Yes.
kind of ironic.
Yes,
Totally
they are
dedicated
flexible.
gauge, but you can measure lots of things with them.
Yep, very quickly and very accurately based on their capability and spec, but they are very flexible.
So it's a challenge to say, is it a dedicated length gauge or is it a flexible measuring device? And I think that's going to play out as we go today as well.
Right. So how does one decide which path to take? Here's a diagram that I'll use just briefly to give us a roadmap. This roadmap starts out obviously with all of us with the product shape and design. What comes from CAD, what comes from the drawing is really going to dictate where we start and where we will go. Sometimes, as I mentioned, in combination of different systems, but with the information that we receive from the GD&T tolerancing, as well as surface finish callouts and other characterization that has to be inspected, we have a roadmap here that takes place. But as you can see, when we break it down, dimension, form, position, roughness, waviness, maybe surface analysis from free curves, many systems today start to cross over with the technologies even. This is very popular if you've just attended IMTS or the quality show. What's happening in the industry, and has been for the last several years, is multi-sensor, multi-probes to make each system, whether dedicated and or on the CMM, more flexible to meet the requirements for whatever job entails. You can see that the 3D CMM bridges dimension, form, and position, but even today that arrow now starts to cross over with surface roughness capability on a CMM, which is available. Or on a form machine, that now starts to bridge over to doing straightness checks, waviness, and actually roughness measurement capable on a traditional form measurement machine. 2D contour machines can do pretty much across the wide spectrum, and then also you can specialize in dedicated surface texture and profilometry that are instrument-based, that are of the utmost in as far as analysis. So it's very difficult sometimes to put a finger on what machine or what instrument needs to be chosen for the right job, but we always have to go back to the product design and look at the features themselves, the tolerancing, the position of where these features are, and we'll talk about some of these key points later on when we decide to look at areas of the sensor, sensing the surface, making decisions properly based on the information we have, how flexible are these systems, how much do they cost, how much do they cost to maintain relative to ownership and throughput, okay? So the flow path chart doesn't always make a clear final decision. We need these more further inputs to make it more clear for us to decide.
I think a quick note on that, Mike, is those arrows continue to grow.
Yes.
Coordinate metrology, the CMM, is all the way down in the roughness domain right now. And we have roughness machines that are measuring contours and dimensions. And at the same time, these are being placed in very dedicated systems.
Right.
So not only do we have these flexible systems, but they are becoming more dedicated.
Right.
And each system is growing in its capabilities.
Right.
These arrows are truly grown far beyond where they were drawn even a year ago.
Yeah, and it just depends on whether the system, the base system, you're building off of an optical platform,
yes,
or where you're building off of a CMM platform,
sure,
or another dedicated system. That structure of the base machine will dictate which path we'll go by adding additional probes. But in certain instances, based on volumetric size of the part, weight of the part, we may have to go to the CMM versus the other dedicated systems. But definitely there's crossover technology that we've been seeing over the years.
Sure.
So here's just a possibility of what can the future show us. And this little video clip will open up some further discussion.
We are not auto-launching this time. Let's go to the previous slide and go into it again. Go up one more, and then down into it.
I think she took control.
Okay, here we go.
Technical difficulty.
Never happens to us. We are not getting the audio from this. So Mike, can you give us a quick description of this application?
So what you're seeing here is a dedicated form measurement machine called a profilometer with a hybrid probe head that allows for surface and contour. But it's married with a robotic automation for part load unload, which you haven't seen much of in the recent past coming from this type of equipment. More or less, this has been started in the CMM realm of the universal CMMs out on the shop floor as well as in the lab for high production. But now, because of the crossover technology and the needs, you start to see the automation take place.
The song is coming through now. You want to sing along? So it looks at the outset to be an incredibly flexible set of pieces used to do something dedicated.
Right.
Great. Well, I think that's a pretty cool example of where measurement is going, where we can be hands-off and get the data all the way through to the end where it showed trends.
Right.
So let's talk about just the concept of a measuring system. We'll start all the way back at the beginning of this flexible versus dedicated conversation. And the fundamental is we are trying to sense something. We're trying to get information about something. That's why we measure.
Right.
Hopefully we're not just measuring because it's fun. I know you and I do that.
Right.
But in general, people measure because they need the information. And at the heart of that is some form of a sensor. Touching, looking, smelling. One of those listening to kind of senses. Most of what we think about in sensors is pretty straightforward technology things, but I'd like to give you a couple of notes on some things that are a bit hidden in the sensor selection. Whether we use a contact probe or a laser or smoke and mirrors, the thing that matters with a sensor is fidelity. Can it measure the thing that you care about? Can it measure the good ones, the bad ones, and the subtle variations in between?
Fidelity, are you referring to like resolution?
Right.
Resolution of the sensor, the gauge?
Not your commitment to your partner.
Right.
But it's things like resolution, but also something like frequency response. If you're to buy a stereo system, you want to be able to listen to all the high notes and the low notes.
Correct.
So buying a measuring system is just like, buying home audio. We're not necessarily going to buy home audio based on repeatability.
Right.
We're going to buy our home audio based on, does it sound really awesome?
Sound good, right.
So when we buy a gauging system, particularly when we measure shape, whether it's roundness, flatness, roughness, we want a gauge that can sense those subtle variations in shape. that doesn't necessarily mean it's repeatable. The most repeatable gauge could be the dead one. Pull the plug, put a big fat tip on the end of it, and it will repeat.
Desensitize.
Desensitize, a great point.
Right.
So if we desensitize a gauge, yeah, sometimes to get one, never mind, you would never do that. So the gauge with the most sensitivity may not be the most repeatable. And that's a challenge, but it is a true fact to this. Another quick point on the topic of sensor that people tend to lose is a new, better sensor can actually cause problems, particularly when your specifications were based on old, dead sensors. So we have to be careful in the metrology community to promote something that's newer and better without understanding the cost of introducing new results that don't compare to old tolerances.
That's a good point. And when I look at OEMs in the business for all the metrology suppliers, CMMs, optical, 3D structured light scanning, sensor technology is where everybody's looking at.
Absolutely.
For the next generation of metrology.
Sure.
I mean,
sure.
CT scanning, that was a big X-ray tomography, computer tomography. It's always going to be the next generation of sensor to dictate what the new metrology trend will be.
Well, and those sensors are getting better resolution.
Right.
So what was once viewed as a flatness number with a new sensor could be a much higher flatness number.
Right.
We're seeing more details.
Right.
And if we compare that to old tolerances, we could be scaring ourselves.
Correct.
Yeah. So we have these sensors, and ultimately another foundation to choosing a measurement system is the decision that we're going to make.
Right.
We buy a measuring system to answer a question.
Right.
Hopefully we do.
Hopefully we do.
So those realms where we're asking these questions could be process control, could be a final inspection, and it could even be in the development of tolerancing. So some of those decision-making principles. In process control, we put sensors and a gauge in place, but the implications are how fast do we need the data?
Right.
Sometimes we're willing to take lesser quality data at the machine. I used to joke that, I only want the best measurement system in the world every time I measure. But then I caught myself because I carry a 6-inch ruler in my backpack.
Right.
And I defile my own principle of having the best measurement system. But what it kind of highlights is the best system might be the one that's close by and good enough. There's a joke in the camera community. For photographers, what's the best camera you have? It's the one I have with me.
Right.
So sometimes in process control, we can live with lesser quality if it helps us catch big hiccups.
Big hiccups, right.
Yeah. Now, final inspection is a different world. Maybe at that point we have some legal implications or some business decisions that we have to make sure the part is right. So there are different levels of accuracy and different concerns at play.
And also maybe further analytical, which takes time to be reviewed in the lab on some feature or based on some process that we need to delve into more for better control. So, the final inspection is where we can see everything.
Absolutely. And another decision-making area we don't think about often is the decision-making that goes into design. Measuring systems have to be chosen for looking at prototypes. And here it's a matter of managing the uncertainty of a measurement system compared to the tolerances you're trying to generate and control. So a gauge decision, flexible, dedicated, is based on those foundations of a sensor and where you plan to use it.
Right. I think also one point to be made here on decision making. So we get this information back from the gauges, whether it's in process, near process, or in the lab, and we get numbers and information from any of these flexible or dedicated systems. But a lot of times that information has to be backed up with a history of supplemental information that I would say relates to maybe functional testing, real-world application to marry the two together and make the right decision for the development of specs to be put on the drawing. So they kind of go hand in hand, and I think many of the standards will talk and address that issue. We just can't look at the metrology report. We've got to actually take those numbers and equate those to other testing. And that is where it helps us also determine, whether the dedicated system is giving us the right information that can correlate or add to the functional testing to give us the right information to make decisions.
Sure. Let me hand it back to you to kind of drive this topic of flexibility.
Okay.
So we have flexible and dedicated, but what is flexible?
Flexibility in the measurement system, we're going to break it down into a couple different areas. Flexibility versus what is to be expected or perceived flexible versus what is real. Okay, because in many instances, we'll buy like a CMM that is very flexible, or an optical measurement machine. They can be, purchased and delivered very fast.
Yeah.
Okay, they're available. But the main thing about the flexible systems are that when there's changeover, we can actually make those changes relative to, work holding and programmability to make another part inspection. But that takes time also, and it takes maybe a skilled operator to make those changes. So even though this machine may be flexible from the capability standpoint, there's additional requirements to make that actually happen.
So there is kind of a myth that a flexible system, let's say a 3D scanner where I paint you with a laser and I have this picture of Mike, I still don't have any information until I do some programming to say, tell me how shiny his glasses are.
Right.
There's still
is this a line feature? It doesn't know. It's a point cloud. You have to define what that information is. So it's very flexible to the standpoint where now you have to add to it from an intelligence standpoint and make determination of what I actually have there.
So the most flexible of systems still require a dedicated analysis to do something with it.
Right. And in certain instances, flexibility on a dedicated system versus a dedicated system, I should say, takes a long period of time to develop the spec for a dedicated system like a hard gauge out on the line. And initially, it's not very flexible because of the constraints of long developed proof of concept, long manufacturer of the product itself. But when it finally comes to fruition and is put into place, it is a system that, from a realization standpoint, able to provide the information real time, and at that point it becomes flexible from the ability to get the data quicker versus the programmable systems that are universal that has to be developed with the program itself time and time again. So the next area is probe access. How flexible is the system relative to probe accessibility? Some small features on part dictates whether we're going to use small styli or large styli, which can be used to scan or inspect larger prismatic parts. But depending on the geometry and the part design and the GD&T callouts, we may have probing issues that will then lend us to the point where we have to go into maybe a contour tracing system with a more sharp conical tip to get into those areas. And then we can come to the point where we cannot see features with tactile that we have got to go non-contact with optical measuring machines or other visual systems. So, probe accessibility may or may not be flexible depending on the system that you're working with.
And that's interesting because as you talk about that, I think of something like a turbine blade, like inside a jet engine.
Yeah.
You'd think it's a very dedicated, crazy, difficult, small feature to get inside some of the jets inside, the little drillings.
Right.
And the only way we can attack those incredibly specific, unique features is with a general purpose system.
Right.
It's the only thing that has the programmability to get into that unique feature.
Right.
Even though it's incredibly unique, it requires general to solve it.
Right.
The dedicated systems can't go there.
Dedicated systems can't go there. And then with that being said, then, we have to make a decision as to a combination system or staying with the dedicated to make that type of inspection.
Building a dedicated set of fixturing around a flexible measurement device.
Right.
Yeah.
Another area that is to be considered with flexibility is how flexible is the system based on the measuring loop. The measuring loop that we're referring to here is, you know, when you're looking at submicron tolerances, you want to have the shortest measuring loop possible, less measuring components within the assembly of the gauge itself, the measurement system. So having less moving axis, a single directional probe actuating to pick up the surface like on a transducer type probe, having the shortest measurement loop may give us the best data possible, but it may not be the most flexible gauge. When we start to look at the more flexible gauge with a measuring loop, at this point now we're looking at maybe 3 moving axis, multiple axis in the probe head itself, analytical calculations that are relative to 3D. So the measuring loop has to be, by basic metrology, the shortest possible to reduce uncertainty. Sure. But there's a little bit of a give and take with what's flexible and what's dedicated and what's achievable with the shortest measurement loop based on what's required.
Well, let's talk about that measuring loop concept again, because I think people that get pushed into metrology don't get those fundamentals sometimes. So one way I tend to think of it is if I were to hold my fingers a ½ inch apart like this, I have a very small loop connecting that measurement from the start to the end of the measurement. But if I try to hold my arms a ½ inch apart, now I have a very large loop and it's unstable.
It's unstable, right.
I can't hold 2 fingers a ½ inch apart through this big loop.
And now when you stand on one leg and hold your 2 arms, now it just starts to compound.
Right. So when you build a measurement system for the highest accuracy, we tend to shrink the loop.
Shrink the loop, right.
And yet we end up with a very accurate, inflexible system.
Right.
Yeah. Okay.
So there's that trade-off as to, you know, the tolerance and to the expected uncertainty and repeatability of the system, and looking at the measuring loop and limiting the measurement loop based on those types of decisions. Fixturing changes are also a consideration for, you know, whether a system is conceived to be a flexible or not so flexible. And lots of times, even on a flexible CMM, depending on the part families that go across a system, there's always going to be fixture changes. The nice thing about the flexible systems on the CMMs is that fixture doesn't have to be so expensive, because all we need to do is have a robust system that's going to keep it secure and give us accessibility to all the features around the part so that we can probe it. So when there's change, we can easily change the fixture and make a programming change, and the flexible system has its payback. Whereas a dedicated hard fixturing system, if there's an engineering change, then it becomes more costly, more time consuming, longer lead time, when we look at fixture changing on those typical parts, and especially if those surfaces are on larger components, larger wingspans on aircraft or aerospace, or, you know, large agricultural type components or castings. Fixturing changes have to be considered truly as a part of whether the system is going to be flexible or not, and whether we want to stay dedicated or stay on a larger CMM. So fixturing changes are critical. CAD-based programming is a big issue today. It's very popular on all the machines, whether it be an optical measurement machine or the CMM or 3D scanning. Getting CAD-based programming is very important to maintain flexibility. You won't have this type of capability when we're trying to compare some dedicated machines, especially hard fixturing. Those are specific for the application and the part, whereas flexibility truly comes in when we look at part programming, and when it's CAD-based part programming, then we have the ability of what's built into the CAD to extract the manufacturing information, the part manufacturing information and tolerancing, and convert it over directly to the part program.
What you're talking about there in the CAD-based side of things actually plays out in 2 areas. One is flexibility of adapting to future needs.
True.
and the other is building up that library of handling lots of parts at the same time.
Mm-hmm.
So there are two aspects of flexibility. Can I handle 6 different part numbers, or can I quickly change it over for next year's part? And the CAD-based systems are certainly helping that.
Yes, yes. And then last but not least in flexibility is, whether the system is programmable. Yep, last one. And programmability kind of lends itself to the CAD-based programming, but it stands unto itself relative to the operator, I'll say. What it takes to program and get that system up and running and launch it, and having the expertise with the operator, with the knowledge base that he has, the experience, the skill set. Do we look internally for that expert, or do we look for outside sources? So how flexible can a system be relative to what costs we'll have for the manpower, the operator, to do this type of capability? Flexibility, the machine doesn't know, other than touching points, what that surface is. We have to create the program, the analysis, and that takes an expert. Whether that expert comes from inside or outside the organization will determine how flexible that system will be and what it can provide for us in our metrology needs.
Yeah, that's one that catches us. I've seen a lot of gauge demos from really, really good applications engineers. So a gauge company will send out their guy and really make it look easy.
Right.
And when that gauge comes in-house and it's time for you to program it, you realize how little you know sometimes.
Right.
And that can surprise you. You have this completely flexible system that only does one thing because you can't make it do anything else.
Right, right. And the fact today, there is so much capability in the softwares that are provided by a lot of the OEMs across the CMM side and the other dedicated systems, surface and form products, vision systems, and optical machines. It takes time and experience to be able to use all the tools that are available and understand what the tools are providing you. You need the knowledge base that supports the answers that these tools are giving you within the programs, and that goes back to standards and other information. So that has to be considered when you're looking at a dedicated hard system and hand tools versus the more programmable systems, which are flexible but need support from the operator. And understanding from the operator.
Yeah. And I'll pick it up here with that kind of flexibility kind of topic on the programmability piece, because that is a cost. Wow, we are not advancing right now. Pam, can you advance us a slide, please, if you have control? Thank you. Go ahead and give us a couple more clicks, please. Do we have control back, Mike?
I think so.
All right. That dirty word, cost. We don't want to think that anything costs when we're buying measuring equipment. Everybody's going to have their own costs, their own cost structure, the things that cost them. I want to talk about a couple of perhaps sneaky hidden costs.
Hidden costs.
One of those,
the ones that will make or break a system.
They will make or break a system, at least in terms of the people using it, perhaps.
Right.
Obviously we have to pay for a system and have it installed and that kind of thing, but pieces that can sneak up on us might be those maintenance pieces. Back to the case where the gauge company brings in their best guy to show you how to use it and install it. And then tomorrow you start pushing the button and you start breaking stylus tips, or you start crashing the laser head and breaking the lens. That never happens in your world, does it at all?
Never.
Okay, well, we could skip that, but it happens occasionally. So cost of ownership also has a piece that sneaks in terms of operator competence, if you will.
Right.
There's a hidden cost of ownership that when you run the machine in your setting, you may be likely to break things more often than the highly skilled guy that sold it to you.
Especially at startup, but it still can continue with employee turnover.
Absolutely, absolutely. There are hidden costs that we may not realize even as you and I develop measuring systems associated with an environment. We don't realize that once a week they come through and spray the place with ammonia to clean it up, and that gets inside our measuring system. because that was never part of a spec. We never designed a gauge based on being sprayed with ammonia, but it was something that came up that we didn't expect. Another situation that comes up is the handoff. And this is in the operator piece, and I see this where a group of people get trained on a new measuring system, and they're trained by the best trainers available. You know, the people who created that measuring device. But the second generation doesn't get that.
And the third generation,
gets even less.
I.e. the third shift.
Third shift, perhaps. Great point.
I.e. third generation is third shift.
Right. Excellent.
Nobody asked us.
Yeah. So there is that longevity of experience, and how does the experience get transferred, which can become very costly in terms of breakage, in terms of cycle time, in terms of the gauge not even being used because it's too hard.
Right.
And a gauge that's not being used is a very expensive paperweight.
Yes.
So there are some psychological pieces that are super important, and I know most engineers, most buyers don't get that shop floor input like they should. You know, put the operator in front of a potential gauging system and hear what they have to say about it. It's difficult in a lot of environments, and it requires a little breakdown of your ego, perhaps, to ask that person that uses it rather than the person writing the check.
Right.
But those are significant hidden costs. I'm going to bring up the dirty word, and some people actually do sabotage measuring systems that they don't want to use.
Really?
Yeah, nice acting memory.
Yeah. I've seen it happen.
But a measuring system that may be the best possible solution that an operator doesn't want, sometimes that system has more problems than it really should.
Right.
So there is a psychological piece to this in terms of cost. A quick topic on our decision making is really what we're using the gauge for, and I like to think of it kind of as gauge throughput, and a couple of quick hidden aspects of throughput that are worth bringing up, because throughput plays real closely to this cost discussion. Throughput is this when do you need the data kind of throughput. Not necessarily how fast are the parts going.
Not high capacity throughput.
Right. Not necessarily that kind of throughput, but I'm talking about information throughput.
Okay.
So how much information do you need at what points in the process?
Right.
So throughput of information, do we need to monitor in real time every part, or would we be confident if we just looked at every batch of parts? Some manufacturing processes will stamp out 100 parts in one chunk.
Right.
So in that case, throughput is the chunk of 100 parts good?
Right.
We're making our decision, our throughput, based on the chunk of one batch. But another kind of throughput model might be if you're making the only one titanium part for the one satellite that's going to go to Mars once.
Right.
In that case,
you only got one shot.
One shot.
Right.
So in that case, a throughput situation is more of per step.
For every op.
Every
op 10's got to be perfect before you go to op 20.
Exactly.
Op 20's got to be perfect before you go to op 50.
Yes.
So at that point, that information is very critical. That throughput and that process of evaluating the data at each op is very critical.
Yes.
Not looking at volume, we're looking at the information at each stage.
Yeah, so information throughput is something to think about. The last thing we don't think about in throughput is we might have a measuring system with a 60-second cycle time. And for example, I have a roundness trace on the screen here. It took perhaps 60 seconds to get that roundness trace. But how often do we find dirt in it? That little spike of dirt in that data made us remeasure. Remeasurement time is another 60 seconds. So perhaps we have a gauge with a 60-second cycle time, but on average, we're cleaning off dirt every other part.
Now, do we see that occur more in a non-contact optical setting versus a contact type?
It's interesting.
I know it's critical for surface and form with a very light, small contact stylus for profilometry and for form measurement, but I would assume that optical, the parts have to be clean.
Well, in optics, we have a different problem. In optics, we have light that reflects and bounces off things and could actually look worse. But in optics, we also have an advantage that it's a new field. So in optics, people have been used to dealing with shapes and forms and dirt, and they often build in removal.
Okay.
So in an optical system, it's not unusual to find pixels that get removed that look bad.
Okay.
But in contact measurement, we tend to look at that and say, darn it, we have to remeasure. So throughput is a big challenge. At this point, we've kind of played out the considerations. I'd like to kind of wrap this up with a few minutes to go here for any questions. We haven't seen anything come in on the chat with just some, what do we take away from this huge amount of information we've shared?
Right.
How do we pull this all together? So I'd like to steer us in a couple directions here. One is, where's it going? So at least we can figure out what to do with it. And any closing thoughts? So where's it going, Mike?
Well, I think one of the takeaways relative to looking at dedicated specialized equipment and when to decide versus CMM is what we've been talking about and touching upon in the earlier part of the presentation up to this point is, you know, where are we going to use the information and where do we need to make those critical decisions along the manufacturing process? Is it going to be in process, in the machine, for immediate control and closed-loop feedback? Are we going to look near process where we have, you know, CMMs and optical equipment next to the gauge or feeding from the line samples, or in the QC lab where the final audit is? So we've got to look at in process, near process, or in the final lab inspection. But all those which do exist today are limited only by the data that we collect. And what's big in the industry and will be for well into the future is how do we handle the data, data management. We see that with all the OEM manufacturers for all the flexible systems, software data management, either online or web-based, or directly as a standalone on the machine. We need to get that information. Even today, universities have set up curriculum and programs called informatics, which are designed specifically to process data. How do we process data, and how do we use that data to make our business decisions? So I think from the gauge standpoints, whether it be dedicated, flexible, even limited, simple tools on the line, all those are at the very beginning or very end of the process of making the part, but getting the information, the data management is going to hold key to how things will be decided in the future and where we go.
Awesome. That's great. And I think that kind of plays into my wrap-up thoughts. Every one of these decisions we make on sensors or measuring loops or devices, flexible, dedicated, is based on how we're going to use the information.
Right.
Closing illustration would be for me, my speedometer in my car. You've got one too, right?
Yes.
I have to watch mine closely because, you know, sometimes I want to get there faster and there might be a police along the way.
Right.
Okay, so in that case, I'm looking at that gauge for immediate feedback constantly. My speedometer is in front of me. It's in my line of sight. I've got this really cool heads-up display.
And you're making decisions based on?
Real-time decisions.
Right.
What's that number on my heads-up display versus the proximity of a police officer? I hope there are no police officers listening.
Okay.
But sometimes, so that would be my dedicated close proximity gauge.
Right.
But sometimes I'm cruising down the highway on cruise control.
Right.
In cruise control, I'm looking every once in a while, maybe when I come up on that slow guy.
Right.
But that same gauge is being used in a dedicated real-time application when I'm hurrying, or it's in a batch process, remote, flexible kind of way when I'm on cruise control. So think about your decision-making as a cruise control decision or a real-time decision in your flexible versus dedicated measurements.
It's a very good point. I never thought of it that way, but that is a very good point. And we're all experienced driving cars and looking at that gauge and using cruise control. And there's a perfect analogy that we can always refer back to.
Yeah. SPC might be just cruise control. Let's hand it back to our hosts in case there were any audio questions that they picked up. So, Mike, are you with us?
I sure am. Thank you, guys. Appreciate your insights on our topic today. I mentioned,
about that audio situation that set us back 5 or 6 minutes here. So, apologize from this side.
Oh, that's okay. That's okay. In the spirit of continuous improvement, we will be sending a very short little survey out to all those who attended our webinar today, and we'd appreciate your feedback on today's webinar. And if you have other ideas or topics that you'd like us to cover, we would appreciate those as well. Again, Mike, Mark, thank you for your time today. Appreciate your expertise on metrology equipment.
Thank you.
Have a great afternoon.